Okay, hi class. So we're finishing up chapter 6, amazingly, right? Chapter 6 is, I mean, it's just a chapter, but it's really getting us prepared for the rest of Trig. Chapter 5 was the introduction of Trig and the unit circle, a little bit of right triangle stuff. 6.1 and 6.2 are about graphing all the 6 trig functions. The sine and cosine are especially important. The other ones don't come up as much, but anyways, we want to finish up the what's in our trig toolkit, and that's using what's called inverse trig functions. And then we'll be able to do anything we want when we're trying to solve and do problems that have trig applications in it. Okay, let me get my screen back up here. Right here. Okay, good. So what we want to do is we want to learn how to, like when we did logs and exponents, they were inverses of each other, so we can use them to solve, to cancel each other out. Well, we need something to cancel out sines and cosines and tangents and all that stuff. And the way we're going to do that is we call them the inverse trig functions. So so remember just the definition of what an inverse meant. Two functions are we'll call them f and g, are inverses if and only if. So they're inverses if and only if their composition, okay, just cancels out. And typically, it'd be like f of f inverse of x, and that would cancel out to be x. So they undo themselves. And so what that also means is that from a domain and range perspective is that the domain of f becomes the range of the other, of f inverse, and vice versa. So let's do that with the trig functions. There's a trig function, there's an inverse trig function for each of the 6 trigs that we've been learning: sine, cosine, tangent, etc., etc. So the domain for a trig function, so these are the trig functions right here. The domain is an angle. It was negative infinity to infinity. Whatever angle you wanted to put into a trig function, you can put it in. There was no, let me get that out of the way, sorry. And the range for the trig functions for sine and cosine, we're just talking about sine and cosine right now, the range was negative 1 to 1. Okay, and this was just the output on the unit circle. It could have been, at pi over 6 it was half, and sorry, root 3 over 2 and comma half, etc. Okay. For the inverse trig functions, they flip. So the domain is going to be the range here. So the domain is going to be negative 1 to 1. And again, this is going to be an output on the unit circle. And the range of the inverse trig function can be negative infinity to infinity, like that. That's a really bad... sorry. Laughing at my infinity sign. Now the problem with that is that this is actually not true. The domain is not going to be negative infinity to infinity, and the reason for that is that we're going to have a little trouble with making something 1 to 1. So it's not actually negative infinity to infinity. It's actually going to be stuck, and we're going to talk about that. But still, the idea is the same. The output of an inverse trig is going to be an angle. But we're going to have to talk about the actual intervals that we're going to be talking about. It's kind of abstract, so let's get it practice. So since sine of pi over 6 is equal to, and if you can't remember that off the top of your head, it's okay. Just draw your unit circle, and pi over 6 is right here, and the x is bigger there, so it's root 3 over 2. And remember, when the angle is small, the sine is small. So since sine of pi over 6 is the y value, is pi over 6, it's 1/2. Okay. What that means is that if I took sine inverse of half, that has to get me back to the angle, and so that's going to be pi over 6. And so the way I read this, let me just kind of just to give you more practice or understanding. When I read this, the way I read it, let's say it's a question mark. This is saying, what angle do I have to plug into sine that's going to give me half? In other words, this is saying, and we could do the math of it, if I took sine of both sides, sine and sine inverse cancel out. They're inverses. So half is equal to sine of the unknown. So that's how I read it when I first see sine inverse of half. This is saying, what angle do I have to plug into sine to give me 1/2? And that's going to be pi over 6. So we have to know our unit circle forwards and backwards. All right, so back over here to pi, cosine of pi. So what's cosine of pi? So just draw that. Pi is over here, and that point is -1, 0. It's cosine is the x value, so it's -1. And so what that means is that cosine inverse of -1, well, again, that's going to say what angle do I have to plug into cosine to give me -1? Well, we just found out it was pi. Okay, making sure my mic works. Okay, so that's how it kind of works. And so they just work forwards and backwards from each other. Make sure I got my pen here. Okay. All right. Now the problem is that if you remember way back when we talked about invertible functions, there's this very special property that a function was only invertible if it had what was called the one-to-one property. So one-to-one. And what that meant is visually is that if you had a graph that looked like this, okay, this is way back in chapter 1. This thing is not one-to-one because remember that fancy test is really easy, a horizontal line test. So it fails the horizontal line test, so it's not one-to-one. And if you're not one-to-one, that means you can't have an inverse because you could have two answers that would give you the go with the x and the y. So that kind of sucks. So for sine and cosine, the question is, are they one-to-one? Can we say they have an inverse? And just so you remember what we were doing back in chapter 6.2 or whatever, 6.1, these guys are definitely not one-to-one. So I don't have room here, but down here, if I graph sine real quick, this is just a sketch. So that's sine of x. Okay, that definitely is not one-to-one, and it goes forever this way too. As you can see, just kind of all over the place. Fail, 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 fail. Fails the horizontal line test over and over and over and over and over again. So that kind of sucks. So what that means is that if we didn't do anything with it, we couldn't have an inverse function because it fails the horizontal line test. But it turns out what we're going to do is we're just going to say, okay, well, I really need an inverse function, so what we're going to do is what's called restricting the domain. We talked about this a little bit back in chapter 1, I think, or I can't remember, chapter 3. And it was the first test. So the restricting domain, what that means is that we're going to say, okay, I need to restrict it so that it only has a smaller domain so that it will have an inverse. Okay. Let's skip this box for just a second. Last time I taught this, people were a little more confused, and it wasn't that helpful. So why don't we just take a look at some examples? I think that would be better. And the way we're going to restrict the domain is, I think it might be more helpful if I write it with the pictures. So leave a little space here. I'm sorry, I don't have the greatest organization for these notes. Not enough space, I mean. But the way we're going to restrict it is for sine inverse, we're going to restrict it, again, I'm using the unit circle to help me. We're going to restrict it so that it has unique answers. So in quadrant 1, all the answers are unique, They're fine. But I can't go over to quadrant 2, right? Because over in quadrant 2, the answers repeat. This y value is the same as this y value. So that second quadrant is no go. But I need the negative value, so I'm going to also have these down here in quadrant 4. So for sine inverse, I'm going to exist in quadrant 1 through 4. So for sine inverse, I'm going to restrict it to negative pi over 2 and pi over 2. So that's going to restrict, so sine inverse. So sine inverse exists in quadrant 1 and 4, and I can put this over here. Sine inverse negative pi over 2 to pi over 2, which just means it's in quadrant 1 and quadrant 4. Okay, now that's for sine inverse. For cosine inverse, it's a little different story because we have to draw a unit circle here for cosine inverse. When we have this, they're definitely unique in this first quadrant. They're not unique over this quadrant, so the same trick won't work. Quadrant 4 doesn't work, so I have to just go over here to quadrant 2. So these are unique because these are the x values, remember, cosine is the x values. And these are different, they're just negative. So cosine inverse is going to be restricted to quadrants 1 and 2. Okay, and that means that its domain would be 0 over pi. Like that. Okay, and tangent is going to be just like sine. It's going to take the answers from sine. So tangent inverse, and the reason for that is that over here they'll be positive, and over here they'll be negative. So tangent will be quadrants 1 and 4 as well. And so that would be negative pi over 2 to pi over 2. Okay, that's all that table was trying to say, but people didn't really like that last time. Okay, so sine inverse is quadrant 1 and 4. It's over here and here. Tangent is, over here and here. So is tangent. Tangent is quadrant 1 and quadrant 4 as well. And cosine, though, is the odd duck. It's quadrant 1 and it's quadrant 2. All right. So let's take a look. So let's get some practice here. So evaluate for A, sine inverse of 1/2. So a sine inverse of half, again, this is asking what angle has to go into sine to give me 1/2. And that answer is going to be sine inverse of 1/2. Wow, sorry, can't draw today. Sine inverse of 1/2. That's going to be pi over 6. Theta equals that. Remember, what comes out of an inverse, sine inverse, is an angle. Okay, so this is asking for B. It's asking sine inverse of negative root 2 over 2. So what angle do I have to plug into sine to give me negative root 2 over 2? And again, you know, I can draw my unit circle here. I want root 2 over 2. That's going to be 1/4 pi, but I need to be negative. Now, I can't go over here into quadrant 3 because that's outside the bounds. The bounds of sine inverse is 1 and 4. So this is only what can come out. So I'm going to have to go down here, and that angle is negative pi over 4. So the theta here is going to be negative pi over 4. Okay? Same deal over here for C. Cosine's saying what angle makes cosine produce negative root 3 over 2? Well, draw my unit circle again. I want negative root 3 over 2. So that tells me it's in quadrant 2 because cosine's negative over here. And I want it to be bigger, so it has to be that one because that will make the x value bigger. And that value is 5 pi over 6. So theta equals 5 pi over 6. And last one over here, tangent inverse of 1. Well, again, that's asking, you know, when is tangent equal to 1? Tangent's going to equal 1 when sine and cosine are the same. So the really question is, when is sine and cosine exactly the same? That only happens once, and that's in this first quadrant at the pi over 4. So that's why it's pi over 4. Okay? So hopefully you're seeing why it's important for us to know our unit circle, because we can't do these things otherwise. And also a quick note that sine and cosine and tangent inverse, they only produce radian measures. They don't produce angles. So unless it's stated in a problem, then we can convert it to a degree. But if it's not stated, then we're going to give the radian answer. Okay? So I'll quickly do these two. So if I wanted to do sine inverse of negative 1, this is asking when does sine equal 1? Negative 1, sorry. And it's equal to negative 1 down here. Now the problem is we can't go past this. On sine inverse there's this big wall that I can't go past pi over 2, so I can't get down there. But what I can do is I can go downwards. And if I go downwards, then I get negative pi over 2. And that's going to be the answer. So sine inverse of negative 1 equals negative pi over 2. And notice I didn't pass that wall. I had to go down to get there. Let's talk about tangent inverse of negative 1. Well, this is where, again, there's going to be a pi over 4, and the reason is that I need sine and cosine to be the same, except I need one to be negative. So it's not going to be this pi over 4 because they're both the same here. That would give me a positive 1. We just did that. But over here, down here, now the y is negative, but the x is still So it's going to be negative, it's going to be root 2 over 2, comma, negative root 2 over 2. And so that's why down here at this angle, which is theta is equal to negative pi over 4, that's what gives me that negative 1, because that divided by that gives me negative 1. Okay, so the answer here for tangent inverse of negative 1 is negative pi over 4. Okay, and when we go over here, so cosine inverse of negative 1. Okay, so again, this is asking when is this, when is the cosine on the unit circle going to be negative 1? So I draw my unit circle. So when is cosine equal to negative 1? So we go over here. Cosine is negative 1. Okay, so what angle is that? So that's going to be over at pi. And notice for cosine, I can go past the pi over 2. It's only for sine and cotangent that I can't go over this, this boundary wall. For cosine, the boundary wall is 0 and pi, so I'm okay. And so then this answer is going to be pi. Okay. And last one, cosine inverse of half. So again, just draw a unit circle. When is cosine equal to half? So it's not at the small angle, because notice the x is bigger here. And you just know our unit circle, so this is going to be root 3 over 2. So cosine inverse of half is equal to root 3 over 2. Wow. Not root 3 over 2, the angle. Sorry, pi over 3. Okay. Sometimes when I record these videos back to back to back, my brain kind of goes haywire. Okay. Now those are for the standard angles, so I knew these were all standard angles because these are all, you know, positions on the unit circle that are these angles that we know. But if we don't have, this is not a standard ratio that comes out of the unit circle, well, what we would do is we just simply use our calculator. So that's non-standard because it's not like a root 3 over 2 or anything like that. But so let's get practice on using our calculator too. But I only want you to use your calculator when it's a non-standard. Okay, so if you did any of the other problems that I just did in that blue box, and you just gave me the decimal answer, that's not good enough for me. I need you to give me the exact answer, which are these, you know, in radians. But this is non-standard, so let me show you how to do sine inverse. Now, I want degrees and radians, so why don't we do the degree one first? Make sure you're in degrees, and then just hit sine inverse. Sine inverse is right here. It's the yellow button. So sine inverse of 0.97. 0 wasn't necessary. And we get 75. Now this is a degree. We're in degree mode, so just remember that that means it's 75.93 degrees. Okay, so equals 75. But we can do it in radians as well. And all you have to do is you have to go back here to mode, radian. Okay, hit quit, and then oh, why don't we get practice? So hit sine inverse. 0.97. I could have just hit second answer, but whatever. Okay, and we get it in 1.325. So theta is that, or theta is 1.325 rads. Okay. This is where we're really going to use inverse trig functions, which is helping us solve problems with right triangle, especially application problems, you know, the dreaded word problems. But they're so useful because, like I said, trigonometry is used in everything, GPSs, cameras, whatever. So we often don't know an angle, so we're going to use these inverse trig functions to help us find an angle. So for instance, take a look at this one. Here's the theta, here's the unknown. This is what I want to find. Okay, and so if I set up a right triangle thing, if I set up a trig ratio, it looks like according to this theta I have adjacent and I have hypotenuse. So since I have adjacent and I have hypotenuse, I need to think, okay, which one of the trig functions involves adjacent and hypotenuse? And I rack my brain and I remember, oh, ka, toa, so it's cosine. So if I set this up correctly, it's going to be cosine of the angle is equal to adjacent over hypotenuse. Okay? And now I need to get my hands on the answer, on the theta. The way you do that is you simply just take cosine inverse of both sides. And the reason we do that is that, remember, inverses cancel each other out. And so now I'm left with theta is equal to cosine inverse of 9/12. And then we'll be able to get the answer. And since the problem didn't tell us how to do it in radians or degrees, we could do it in degrees if you want. So typically on our triangle, we're used to degrees so much. So we'll just do cosine inverse 9 divided by 12. And that's our angle. So our theta is 41.41-ish. And notice that I put a degree sign here to let me know that the answer was in degrees. Okay, and it's to define an acute angle. It's about 41. That's good. So we did that with cosine. Could we have done it with something else? Not really, because say we wanted to do it with sine. Would sine work? Well, sine of theta would be opposite, and I don't know opposite. So I just call opposite over 12. So I wouldn't be able to do sine inverse because I had this unknown side. I don't want two unknowns, unknown side, unknown angle. Now, of course, you could do Pythagorean theorem. Once you do Pythagorean theorem and solve for this side, then you could use sine. That's fine. But this one I just use cosine because we already had the adjacent and the hypotenuse. So speaking of sine, how do we do this one? Okay, well again, here's the angle. Here's what I want to know. 6 is that the adjacent or is that the opposite? Well, that's the opposite. And 10 is the hypotenuse. Okay, so that means that I have opposite and I have hypotenuse. Well, that's so. So that's sine. So that means that sine of theta has to be equal to opposite over hypotenuse, like that. I mean, you can simplify if you want, it's 3/5, but whatever. Because I'm just going to take a sine inverse of both sides. Those cancel. Oh no, hold on everyone. We're back. Little scary there. I thought I had lost everything, but we're back. Okay, we're close to being done. One more page anyways. So here, sine inverse of sine of theta. Okay, those cancel out. And we're left with what we're going to actually calculate. Theta is equal to sine inverse of 6/10. Which, we can stay in degrees if we want. So we're in degree. And we just do sine inverse of 6 divided by 10. Like that. 36.87. Okay? So that's how big that angle is. Now again, we couldn't do cosine here because we didn't have adjacent. But we could do Pythagorean theorem and find it. And we're going to get the same answer. Okay, so the last little thing we want to do is just talk about composition again. We want to make sure we understand what inverse and sine means. Now, so technically inverses undo themselves. So is this true that sine inverse of sine is equal to this? So we would think so because they're inverses, right? So they should cancel out, right? Well, it turns out no, this is not true. And the reason is that, remember, this is outside the domain. Okay, for sine of sine inverse. So sine and sine inverse. Because remember, we talked about that when I'm doing sine, I only want to go from here to here. I'm doing a red line. I only want to do it from here to here. Negative pi over 2 to pi over 2. So you just got to be careful. This 5 pi over 4 had to go past this restriction, this wall. So no, so that's outside the domain. So I can't even take a sine inverse of that because it's not going to be allowed because I had to jump this bound. So you just got to be careful, okay? Because remember, we're restricting the domain. So just to recap just what I did on the first page. Sine inverse, okay, that restriction is negative pi over 2 to pi over 2, okay? Cosine inverse, that restriction was 0 to pi, and tangent inverse, that restriction was same thing as sine, negative pi over 2 to pi over 2. And I'm also kind of visual, so sine, that's quadrant 1 and 4. This is quadrant 1 and 2. And this is also quadrant 1 and 4. Okay. All right. So let's go ahead and take a look. So do some of these problems. So sine inverse of sine of pi over 3. Now this is in the domain, so it's okay, because pi over 3, you know, is that in the correct quadrant? Pi over 3, yeah, you betcha. So that's okay. So that's not a problem. So I can just simply say, okay, if I did sine inverse of sine, those should cancel out, and so I should just be left with pi over 3. All right. Now here, what about this one? This is a problem though. Sine inverse of sine of 2 pi over 3. Well, that's actually outside my domain because, you know, that's in quadrant 2. Sine inverse can't be in quadrant 2, so that's over here. So, uh-oh, what does that mean? Well, it means we can't actually technically do it. We can still get an answer though, because we could say, okay, sine of 2 pi over 3, what is that value? So that value, that coordinate is negative 1/2, comma, root 3 over 2. So if I take sine, this is actually like saying sine inverse of positive root 3 over 2. So we just got to find the answer. Okay, what is sine? What angle? So this is what this is saying. Sine inverse of root 3 over 2. So now the question is, what angle makes sine produce root 3 over 2 in quadrant 1 or quadrant 4? So that's the reference angle, which would be pi over 3. So we just have to be careful when we're dealing these sine inverses or sines, that we make sure that we refer back to the correct domain. Cosine inverse and cosine. So here, that's okay. That is in the accepted domain for, this is the accepted domain for cosine inverse between 0 and pi. And cosine inverse, so that means 2 pi over 3 is over here, so that's okay, that's allowed. So we can just simply cross out, and so we get the answer 2 pi over 3. Okay, we got one more, this negative pi over 3. So this is a no-no, okay, no-go, because the accepted domain, again, was here, right? Negative pi over 3 is like way down here. But again, we can just take a look at it. So we have the x value is going to be smaller here, so it's 1/2. The y value is going to be bigger, so it's going to be negative root 3 over 2. I don't really care about the y value, I just care about the x value. So 1/2. So this is saying cosine inverse of 1/2. And that tells me, okay, cosine inverse of half. What angle, when I plug it into cosine, makes it half? And that's going to be up here. That's going to be the pi over 3. Okay, and so that's why this answer is equal to pi over 3. And then we just got to ask ourselves, are we in the correct domain? Are we in quadrant 1 or quadrant 2? Yeah, we are. This is pi over 3. So that's okay. So that's in the acceptable domain. All right. The last little things we want to do is we can use right triangles to help us solve. This is a non-standard one, 4 over 5. It's not on the unit circle. You know, there's the only thing on the unit circle is 0, 1, 1/2, root 3 over 2, and root 2 over 2. So 4 over 5 is not on the unit circle. But I know I can do some stuff to do this, because let me draw a right triangle here. Here's theta, here's right angle. Let me just put a theta here. And so remember that what comes out of this is an angle. Cosine inverses produce angles. So if I call this an angle, this is saying the theta had a cosine of 4 over 5. So that means that the adjacent leg is here. Okay, and again, that's because cosine is talking about adjacent over hypotenuse. So that must be the adjacent leg, and that must be the hypotenuse. So the adjacent leg's here, the hypotenuse must be here, okay? And so that means I can solve the triangle first using Pythagorean theorem. So call this I'll call this b, I guess. And so I know 4 squared plus b squared has to equal 5 squared, which tells me 16 plus b squared equals 25, which tells me b squared is equal to 25 minus 16, which would be 9. So b is equal to 3. That's called a Pythagorean triple, by the way. It's a good one to have handy. 3, 4, 5 triangle. Pythagorean triple means all the sides are whole numbers. Okay, so now that I know that that's 3, I figured out the question is really just asking me what is sine of this angle. Well, sine in this triangle is gonna, for that angle, is gonna be opposite over hypotenuse. So it's gonna be opposite over hypotenuse, which is 3 over 5. Okay. So get rid of that. Don't need you there. Okay. So we figured out that even for a non-standard triangle, non-standard angle, excuse me, we figure out that we could solve it. It's 3 over 5. Okay. And we could do the same thing over here. Let's use a right triangle to find an exact value. Notice I want exact value. You could just plug this in a calculator, but I want the exact value. So tangent inverse of 7 over 4. Well, just remember that tangent inverse here, this is going to be a theta. So I recommend drawing a triangle. There's a little more room here, so it's a little easier to draw. Okay, theta here. So here's my theta, and tangent of that theta is going to be, remember, opposite over adjacent. So remember, tangent of an angle is opposite over adjacent. And they told me that it's 7 over 4. So that tells me 7 is the opposite and that 4 is the adjacent. So 7 is the opposite, 4 is the adjacent. Well, just like last time, let's go ahead and solve this hypotenuse here. So it's going to be 4 squared plus 7 squared equals c squared, which is going to be 16 plus 49 equals c squared. And that tells me 16 was at 59. Yeah, 65, right? Yeah, 65 is equal to c squared. And then we just take a square root. So then we get c is equal to the square root of 65. Okay, so that tells me that's root 65. Now what that means is that when we want to find sine of the angle, because remember this is an angle now, so we want to find sine of the angle, it's just going to be opposite over hypotenuse. So opposite over hypotenuse, and that's going to be 7 over root 65. And just like I said in the notes before, it was very funny. I'm recording this in spring of 2017, but more than one person on our exam said we're not savages, so that means it's good. The things I say are sticking. So we're not savages. We don't leave radicals in the bottom. Okay, we rationalize our denominators. So we go ahead and rationalize that, and that gives me 7 root 65 divided by 65. Like that. So we figured out that sine of tangent inverse of 7 over 4 is equal to that. And that's the exact value. We could get this on a calculator, but it's not going to work out correctly. So it's not going to give us the exact value, I should say. So you have to use a right triangle. Okay? I'm going to try to give you hints when I say use a right triangle, but if you don't know when you need to use a right triangle, just remember that these are non-standard angles. So that's why I had to do this. I had to use these right triangles. Okay, that's it, folks. Thanks for watching. That's the end of chapter 6, and I'll see you next time.